guys, welcome back. Okay, hope you're doing well. This is our next lesson, independence, multiplication rule, and conditional probability. I broke this up into two lessons. Okay, so this video is only going to cover the independence and multiplication rule, and then sometime later on, we'll start talking about conditional probability. Okay, so PowerPoint slides are up there. You can print them out, write on it, or if you'd like, you can just take separate notes. That's entirely up to you. Have a calculator handy, and let's get started. Okay? Some vocab. Okay, a compound event is a composite event consisting of two or more simple events. Boy, that really clears things up, doesn't it? All that means is that when I pick a card out of a deck of cards, I'm picking more than one. I'm going to pick twice. Or I'm going to pick 3 times. Okay? Or I'm going to flip a coin and I'm going to roll a die. Sorry, I blanked out there, okay? So we're talking about multiple things happening. And in these events that are happening, there's classifications. So for instance, if we have independent events, it's the probability that A occurs, and it does not affect the probability that B happens. So going back to my last example, does flipping a coin affect you rolling a 3 on a die? No, right? One thing, it's not the same object, but the probability of the coin is not going to affect the probability of the die. Okay, they're different. And then dependent means the probability of A occurring in some way changes the probability that B will occur. Okay, what does that mean? Well, let's think of it this way. If I draw a card out of a standard 52 deck of cards, I don't put it back. I draw another card out of the deck. Now I have less to choose from now, right? I have 51 cards left to choose from. So that's going to affect the odds of me selecting my next card. So for instance, if I drew a king the first time, what are the odds of me drawing a 10? If I still kept the king out of the deck, well, I got less to choose from, so the odds will change a little bit. So they affect each other, okay? So let's try this out. Determine whether the event is independent or not and explain your reasoning. First one, you flip a coin and roll a die. Would that be independent or dependent? Okay, that's going to be independent, right? The odds of you getting heads on a coin does not affect you getting a 1 on a die. Those are independent events. They don't affect each other. Okay, part B, earning a bachelor's degree and earn more than $100,000 per year. This could go both ways, okay? Some people could say this is independent because there are people out there who do not have a bachelor's degree and they're earning more than $100,000 per year. Doesn't seem fair, does it? Okay. But some people might say dependent because sometimes you need that education, you need that degree to earn the big bucks, to earn $100,000 or more. Okay. So it depends. You can actually make cases for both of them. All right. And then for the last one, a card is selected from a deck of cards. You don't put the card back, then you draw another card. Okay? That one there would be dependent because I have less to choose from the second time I draw. Now A and C, I didn't realize I put those on there, so I used those examples again, but still, it's there for you, good solid example. Okay? So how do we actually calculate this stuff? Well, if we want things to occur at the same time, okay, meaning I want this to happen and I want this to happen, and this and that, I can keep going. It doesn't have to just be 2 options. We multiply. So notice we have a new word, not or, here we have an and. Okay? And means I want them both to occur. And to do that, we're going to multiply those 2 together. Okay? If it's more than 2 events, then we just keep multiplying things. Okay? Let's say I draw 5 cards out of the deck, and I want them all to be, well, I'll tell you what, not 5. Make it 4. Let's say I draw 4 cards out of the deck, and I want them all to be aces. So I'd multiply the outcomes for all 4 aces. Okay? There's more involved with that, but just a very broad example. Let's take a look at one. Speaking of examples. Suppose you flip a coin, a fair coin, all right? You always hear that in math problems. make sure it's a fair die or a fair coin, meaning you don't want something that can tip the odds in your favor or against you. Okay? So you flip a coin twice. What's the probability that you obtain heads on both flips? Okay? So I'm going to go ahead and use our notation. Probability of getting heads twice. You could say it that way, or we can use the and, heads the first time, and heads the second time. To be honest, there's way too many ways of writing this, okay? There really is. And actually, too big of a fraction part there, sorry. So, what are the odds of you getting heads the first time? It's going to be 1 out of 2, right? There's only one head side on a coin. Times. Now, let's say that happened. Let's say you actually got heads the first time. What are the odds of you getting heads the second time? It's still the same, right? 1 out of 2. I want these both to happen, so we multiply. So we multiply those two together. We get a fourth, 4.25, which is 25%. So many different ways of writing this. The decimal version and the percentage. Okay? So going back, why multiply something? Why aren't we just adding these together? What's the difference? Well, remember, when we did the addition rule, there was more items in the sample space I wanted to select. So the numerator got bigger because of it. There was more items to select out of a total. This is different, okay? I want the first one to be heads. It's only going to happen 50% of the time. Out of that 50%, okay, out of that sample space, it already shrunk a little bit, right? So out of that small sample space when I did get heads, what are the odds of those? You know, what am I tacking onto that sample space is I want another, heads. I want it to happen again. So I'm going to take half of that to make sure that I have heads again. Okay? So you're almost taking half of the first thing again, or a third, or whatever the number is. Okay? So it's different than adding. Adding is just, I want all this to happen once when I draw, okay? And I want more things included, that's why I'm adding. In this case, I'm multiplying because I want multiple events to occur. Okay, I'm going to do more than just one coin flip. I'm hoping that explanation helps a little bit. Okay, roulette. In a game of roulette, the wheel has 0, 0, 0, and then 1 through 36. We had a problem like this on the homework, so this should look familiar. So a metal ball is rolled around the wheel until it falls into one of the numbered slots. What's the probability that the ball will land in slot 17 2 times in a row? Before you even calculate it, do you think the odds are even going to be remotely possible? Probably not. It's going to be very slim. Think about it. You have 38 different possibilities, and you're saying you want the most specific possibility to occur twice out of that 38. So already ahead of time, you can think about it like, oh, wait a minute. This should be a small number. If I get a large number, something went wrong. So the probability of 17 and another 17. Okay? So what are the odds of you getting 17 the first time? Well, it's going to be 1 out of 38. Still, same as probability, right? There's one number out of 38. That is 17. And then what are the odds of you getting that the next time? 1 out of 38. Okay? Notice, these events are independent of each other, right? You getting this the first time doesn't affect you getting this the second time. Okay? Multiply those across. 1 out of 1,444. Okay? So as a decimal, here's what you get. It's very slim. If you ever play roulette, it's probably not a good idea to place all your money on one number back to back to back. Can you imagine if you did this a third time? The odds of you getting all 3 in a row to work like that is just astronomical. It's not going to happen. Okay? Usually I ask questions, but if If you do have questions, you can email me. Okay? Moving on. Okay, in science class, students are drawing marbles out of a bag to determine lab groups. Not that I think this happens, but it's a good example. It makes its point. There's 4 red marbles, 6 green, 5 yellow in the bag. So Ashley draws a marble out, not liking the outcome. She puts it back in, draws a second time. That's a real nice teacher. What's the probability that each of her 2 draws gives her a red marble? Well, that'd be a lot of bad luck, right? You don't want red. You pick it the first time. Nope, put it back, pick it again. Okay? What are the odds of that happening? So, once again, we use notation, probability of red and red. Okay? So, now we plug in the probabilities. The odds of you getting red the first time. Well, there are 4 red marbles in the bag that you could select from. Out of a total of, I think that's what, 15? There's 15 in the bag. Okay. Now these are independent of each other because she replaces the marble, right? I'm going to have the same probability here. Nothing changes. There's still 15 left. There's still 4 red. Okay. So divide those, or not divide, multiply those, I'm sorry. 16 out of 225. Which would be 0.071. Or, I mean, I should write as a percent, right? 7.1%. Either way. Okay. So it's not very likely for her to draw red twice out of the bag. Okay, it's more likely for her to draw a different color, possibly. Or draw 2 different colors. Okay? So what would it be? I'm sorry. Choice is D out of that group. Forgot it was multiple choice. And once again, these guys are independent events. Okay? They don't affect each other. Let's do another one. I know, I have a lot of examples here. This is the last one, I promise. Life expectancy. Okay, the probability that randomly selecting a male that's 24 years old that will survive his whole, year to 25 is 0.9985 or 99.85%. So yeah, he's got a good chance that a 24-year-old male would make it to his 25th birthday. Okay? This is part of the National Vital Statistics Report, so I put the source there. If you want to see it yourself, it's pretty interesting. I never realized that, they actually make this calculation. Kind of grim in a way, right? So what's the probability that 3 randomly selected 24-year-old males will survive the year? Okay? And then the last one says, what's the probability that 20 randomly selected 24-year-old males will survive the year? Okay? That's the goal. Now, notice something. I don't really have, okay? I'm not saying that you pick a guy and you keep him. You don't put him back into the population or anything like that. So we're just assuming that these are going to be independent of each other, okay? Just for ease and not, get too messy with it. So let's try it out. Okay. Probability that 3 survive. Now could I say 1 and 1 and 1? Can I use the ands? Yeah, but we're going to shorten it. Okay, we already know ahead of time this is your independent events right now. Okay, so we're going to have, 0.9985? That's the odds that the first person I select survives. He's good. The odds that a second person that I select survives. Same thing, right? Doesn't change. And I'm going to do it one more time, okay? Same thing. Okay, nothing changes. You could abbreviate it, shorten it. You could just write it as an exponent. Either way, just do it to the cube power, okay? So what's this come out to be? Well, it comes out to be 995 or 99.5%. Okay, depending on where you round or how far you went with it. So you have a 99.5% chance that you select 3 males at 24 years old to survive the year. Okay, that's a good thing. So think of it this way: if you're, years down the line when you turn 24, the odds of you surviving is pretty good until they update different variables and different factors and stuff, and just how the year goes. Now, look at part 2 of this. The probability that 20 will survive, that all 20 of them that you select. Now, I could write out that probability 20 times, or we can shorten it and just do this to the 20th power. Okay? Now, I want you to think about something for a second. I'm selecting more people this time. What do you think is going to happen to the probability? Should decrease, right? Just like the coin flip problem. Me getting heads the first time is 50%. Me getting it twice in a row went to 25%. The more trials or the more time you select something increases, the lower your odds are going to be. Okay? So when you're calculating this stuff and you're calculating something that's happening 20 times, more than likely, it's not always going to happen, right? Unless it's luck. There's always that small percentage of luck where it could. So to the 20th power, so this is our final result, or 97.04%. Okay, so, our prediction was right. It did drop a little bit when we selected more people, okay? Any questions on that? I'm so used to saying that. Like I said, if you have questions, always try to contact me. Okay? All right, last part. This is called the general multiplication rule. Okay? And this is going to start encompassing dependent events. Okay? What happens when things do affect each other? Okay? So we're still going to multiply, but look at that notation over there. Okay? What does that read? So in other words, the probability of E and F is the probability of E occurring times the probability of F occurring given that E happened. Okay? Because they affect each other. So, let's say you drew a king out of a deck of cards. Good, that's what I wanted. I want to draw an ace the next time. So, given that this happened, I got less to choose from. Now I'm going to draw again, and those odds and the total cards in the deck are different. Okay? So that's what we're going to look at for the next couple examples. So that's what this is. The word given is literally this vertical bar. Okay? So calculate F happening given that E already happened. Okay? So let's go back to the science class example. Lab groups again. This time we have Graham, draws a marble, does not put it back this time. Then his friend Mina draws another marble. What is the probability they both draw green marbles? These are dependent events because it's going to affect what Mina draws now. So the probability of green and green, it's a little different. So if you want to put underneath it, these are dependent events, so that way you can tell what the difference is. Okay? First one, how many green marbles do we start off with? 6. How many total are in here? And I think it's still 15? Yeah, 15. Okay? Now we're going to switch it up. He doesn't put the marble back. So there's only 14 left. Let's say he did choose a green one. How many green are left in the bag now? It's not 6. It's going to be 5. That's why this is dependent. This affected Mina's chances of getting a green marble, right? That's why it's dependent, okay? And that's why the totals for this change as well, Okay? So multiply these out. You get 30 out of 210. And if you reduce the fraction, you get 1 over 7. Now, could you do a percent? Absolutely. The reason why I didn't is because if you look at the multiple choices, well, they're all fractions. So A would be the correct answer, 1 out of 7. Anytime you have a fraction and you're going to leave it as a fraction, make sure you reduce. So there's a 1 out of 7 chance that they both draw green. Okay? Okay. Card probability. 3 cards are selected from a deck of 52. What's the probability that all 3 cards are diamonds if neither the first nor the second card is replaced? So probability of a diamond, and a diamond, and a diamond. So we got 3 things we're drawing. So we're going to have 3 fractions. This is a dependent event problem because we aren't replacing the cards. The sample space has changed after I draw it. So, how many diamonds are in a deck the first time? Well, there's 13 in each suit out of 52. Just like that. Okay? Next, let's say he did draw the diamond. Now there's only 12 left in the deck, and there's less cards in the deck, so now there's 51. Continue. He did pick a diamond again. Now there's 11 diamonds in the deck, and now there's only 50 cards left in the deck. Okay? If he just picked once, this is the fraction we're using, right? But because we're drawing 2 more times, you see how the odds of this happening might not be that great? So keep that in mind, right? We talked about it before, but this is just another way to break it up. Okay. So multiply those across, 1,716 over 132,600. Okay. Or 10129. I'm sorry, I should put the percent. We'll say roughly 1.3%. Move the decimal over a little bit. And we round. Okay. So 1.3%. He draws 3 diamonds in a row. Okay? And like I said, it doesn't mean he can't. The odds could be good depending on how he shuffles, right? If he didn't shuffle a deck that well, maybe all the diamonds are grouped together. It just depends. Okay. I have one more problem, and this is it. Okay, sickle cell anemia. So let's do something a little bit more application-wise, because a lot of people don't mess with cards. A survey of 10,000 African Americans was determined that 27 had sickle cell anemia. Suppose we randomly select 1 out of the 10,000 African Americans surveyed. What's the probability that he or she will have sickle cell anemia? Okay, so let's figure this out. We're only selecting one of them, so this is back to just straightforward probability. Nothing addition-wise or multiplying-wise. So the probability that one person has sickle cell. Okay. So there's 10,000 of them in the survey, and there's 1 out of 10,000 that have it. Okay. Well, actually, I'm sorry, not 1. 27. Sorry about that. I just looked at the PowerPoint and saw the word 1, and I just wrote it down. No, there was 27 out of there. Okay. So we divide. And we get this as our final result, 0.0027, okay, or 0.3%. Okay. Something along those lines. Not very likely. I mean, 27 out of 10,000. That's for you to select one of them. Yeah, large sample space. Now we're going to make a comparison. Look at Part B. Part B says what's the probability that 2 individuals from this group are selected. Okay, so we got 2 people. Now I probably should have specified, but in this case, unlike the last one that we looked at, we're not going to select the person and then put them back in the group. Okay. So the first probability would still be 27 out of 10,000. But let's say we did pick that person. Now there's only 26 in the group out of 9,999. So this is dependent. Okay. So multiply these. You're going to love this. It's 702, 9,999,000, I think. 1, 2, 3, wait a minute. I'm trying to read my notes here. Boom, boom. So 99,999,000. 990,000. Sorry, I misspoke. So before I give you the decimal answer of this, what do you think? Think it's very likely to choose 2 in a row? Not really, huh? So here it is. Those are the odds right there. Not very likely. Now let's make a comparison. Look at this. Look at this. If I select one once out of the group, I have a higher chance of getting someone, not much, than if I select 2 people out of the group, right? And we made that observation before. If I selected 20 people out of the group, it's not likely that all 20 in a row is going to have sickle cell anemia. Okay? Alrighty, guys. I think I got one slide left. Okay, if 2 events, E and F, are independent, okay, then the probability of E happening given F has occurred, that doesn't affect nothing. It's just the probability of E. Okay? So remember, this right here, I don't want to draw on the TV, but this right here, if it's independent, I don't worry about this. I just calculate E normally. So going back to that, going back to this equation, this is if they're dependent events. But if they're independent, then I get rid of this part and just calculate F normally. Okay? So it's important to know how to read these formulas and how to interpret and understand them. And what happens if a 0 is here or if a 0 is there, what does that mean? All right? So that's it. Those are independent, dependent events. If you have any questions, please let me know. Hope you guys have a good day.